Hi everyone. In this module, we learn the concept of Nmr Spectroscopy. This is Unit 5, Block 2, 3rd semester's MSc Chemistry in Karnataka State Open University. In this unit, we discuss the basic introductions regarding to that, nuclear magnetic resonance spectroscopy, populations of energy levels, resonance phenomena, relaxation. The spin lattice relaxation means longitudinal relaxation, transverse relaxation means spin-spin relaxation, NMR instrumentation, local magnetic field around a nucleus means shielding effect, chemical shift, and unit of chemical shift, influence of electron density on chemical shift, spin-spin splitting in proton NMR spectra, some general rules for spin-spin interactions, effect of magnitude, coupling mechanisms, measurement of coupling constant, different types of coupling constant observed in organic molecules, the geminal spin-spin coupling, vicinal spin-spin coupling, and torsional or dihedral angle, vicinal valence angles, bond length, and some importance of these organic compounds. First, we know that NMR means the nuclear magnetic resonance. It is discovered in 1945 by two physicists, Bloch and Purcell. The physicists were mainly interested in resonance, did not devote much attention to structural analysis. Soon after finding an NMR signal, chemists realized the importance of these techniques and started NMR spectroscopy in the structural analysis of molecules. In 1953, first low resonance NMR instrument was released on the market. The first NMR instrument consisted of the magnets, for which the magnets were 1.41 means 60 megahertz, 80 megahertz, 90 megahertz, 100 megahertz. After 1940, the superconducting magnets with high resolutions which work at the temperature of liquid helium were produced. Nowadays, we have to use that 200, 300, 400, 600 megahertz NMR instruments. Currently, now we are using 900 megahertz NMR instruments is under construction. Besides chemists, the NMR instruments are also utilized by physicists, biochemists, pharmaceutical chemists, and medical doctors. The professionals make use of these techniques to elucidate structural information and the physical properties of a molecule. The use of NMR analysis in the field field of medicine is becoming commonplace for the identification of medical treatment of certain disease. As a result, the use of X-rays will soon become obsolete in the near future. What are the reasons for popularity of NMR stems from the fact it works with radio frequency waves. That radio frequency is not a hazardous to the people health. It can distinguish soft and hard tissues. Besides an anatomical information, physiological information can be obtained. In recent years, the routine measurement of Nmr spectra of elements such as phosphorus, sodium, potassium and nitrogen have been studied. It is like that these techniques will find applications in medical area rather than so. For instance, sketching the phosphorus distributions of a tissue slice. The nuclear magnetic resonance spectroscopy is based on the magnetic properties of atomic nuclei. Atoms consist of a dense, positively charged nucleus surrounded at a relatively large distance by negatively charged electrons. This nucleus spins on the nuclear axis and the circulations of nuclear charge generates a magnetic dipole along the axis of rotations. The intrinsic magnitude of dipole generated is expressed in terms of magnetic moment. This moment is a vector and has definite values which are quantized. The spin quantum number of proton and carbon nucleus is half. The corresponding magnetic quantum numbers are plus of and minus. Since the proton has two different magnetic quantum number, it has two different energy levels in the presence of static magnetic field. Two different alignments in the magnetic field. The absence of strong external magnetic field, the nuclear spin of protons are randomly oriented. When a sample containing protons is placed in a static homogeneous magnetic field, the magnetic field mu of protons will interact with the external magnetic field and the nuclei will adopt a specific orientation. Just to see that here, the nuclear spin will align parallel with the external magnetic field and some anti-parallel. Just to see here, orientation of magnetic moments of proton in the absence of magnetic field. It is moving in that randomly. It rotates in that anti-parallel. But in the presence of magnetic field, the align its parallel. Okay, like that. The energy of the nucleus spins that are parallel oriented is lower than that of those spins that are anti-parallel oriented. Just to see here, energy level schemes for nuclei with spin nuclear energy. N is equal to 1. Here, M1 minus 1, M is equal to 0, M is equal to plus. The energy difference between two energy states is very important in Nmr spectroscopy. The energy difference between the states increases with increased strength of the magnetic field. The increasing the energy delta E will be reflected in the sensitivity of the Nmr instruments. Just to see this, the energy difference delta E between two adjacent levels as a function of applied magnetic field. The population of energy levels according to the law of thermodynamics. If there are two different energy levels, the population of these levels has to be different. Therefore, when sample is placed in a magnetic field, the nuclei will distribute themselves between the different energy states in thermal equilibrium. This distribution of nuclei between two states is given by Boltzmann relations. What is that Boltzmann relations here? N alpha by N beta is equal to e power minus delta E by kT. Here N alpha is the number of nuclei at excited state, N beta is the number of nuclei at ground state, delta E is the energy difference between the K, Boltzmann constant, and T is what? That is temperature. Next we consider here the energy difference between two energy states built up by a magnetic field is very small. The population's excess can be determined using the above equation. What is that? We consider N alpha by N beta is equal to 0.99984. What it means here? Suppose we assume that 4,03,000 molecules are there. Among the 2,00,000 of them populate excited state and the remaining is in that ground state. Here two states. This is what? Ground state, this is what? Excited state. In that excited state, 2,03,000 molecules are there. In that ground state, in that excited state, only 2,00,000 molecules are there. The population excess in ground state only. What? 3. This excess determines probability of a transition and thereby sensitivity of the experiment. If the populations of the two levels were exactly the same, the number would be equal and there would be no net absorption of energy. In case of we do not absorb in that Nmr signal. This is the irrespective of measuring techniques used. Sensitivity is a very important aspect of Nmr spectroscopy. The signal intensity is directly proportional to the ratio of the protons populating to energy levels. The greater the population excess at lower energy level, is the greater is the probability for the resonance. The number of the resonating protons in some way increased, the signal intensity is also increased. Now we are going to the point of what? Resonance phenomena. Resonance phenomena means if the oriented nuclei are now irradiated with electromagnetic radiation of a proper frequency, energy absorption occurs and the lower energy state slip to the higher energy state. The populations of nuclei at lower and higher energy state is equal and this process is called the resonance. Next, relaxation. relaxation means after resonance, the populations of different energy levels will be changed. The resonance of nuclei at the lower energy level is reduced. Simply we say that relaxation means in order to maintain the slight excess of nuclei at lower energy level, the nuclei at the higher energy level lose their energy and return to the lower energy levels. And this process is referred to as that resonance phenomenon. If you see here, this electron gaining of energy in resonance. This one, this is the block diagram of this relaxation process. Here, relaxation process can be divided into two categories. One is that spins lattice relaxation, simply that is longitudinal relaxation, represented by the symbol is T1, and spin relaxation, that is transverse relaxation, represented by the symbol is T2. What is spin or spin lattice relaxation? Simply that is longitudinal relaxation. The excitation occurs by the absorption of electromagnetic radiation. The probability of spontaneous emission of the excess energy in the form of electromagnetic radiation is negligible. Before we start to discuss the spin lattice relaxation, the term should be defined. Lattices are defined as all kinds of aggregates of atoms or molecules in the solution. The solvent molecules dissolved gases are also considered to be lattices. Please go through that. The spin lattice relaxation designed by the time T1 involves the transfer of energy from the excited protons to the structural protons to the surrounding lattice. The energy will be transferred into kinetic and thermal energy. The magnitude of T1 varies to a considerable extent depending on the nucleus of its environment. Liquids usually have T1 of 10 to the power of minus 2 to 10 to the power of minus 3 seconds, while in solids value is much larger, means here T1 is less than 1 second. This is spin relaxation or transverse relaxation, represented by the symbol is capital T2. The spin relaxation characterized by the time T2 involves the transfer of energy among the processing protons. The most important features of spin relaxation is that it determines the natural width of the line in the spectrum. The relationship is described by Heisenberg uncertainty principle, which states that the product of uncertainty of the energy delta E and uncertainty of the lifetime. So what is that uncertainty principle? Delta E into delta T is equal to h by 2 pi. Substituting delta E is equal to delta E is equal to h into V. Finally, what is that delta V? 1 by 4 pi r into 4 pi, like that. This equation shows that relationship between peak width and relaxation time. If the life is very short, the uncertainty is energy will be lost. The uncertainty in energy is in turn manifested in an uncertainty in the frequency. In short, delta T is small, then delta V is large, and the peak is therefore broadened. Now we are going to discuss with NMR instrumentation. NMR instrumentation. Two types of NMR spectrometer based on different designs are now used. The CW and FT spectrometers. The basic requirements for all high resolution NMR spectrometers as follows. A magnitude capable of producing a very strong static and homogeneous field. A stable radio frequency generator. A radio frequency reviewer. And finally, detector. These are all what parts of NMR signals. Here, radio frequency transmitter, sweep generators, and radio frequency receivers, recorder, spectrum, and magnet. Here, the magnet is necessary to produce the different energy levels. Mainly paraments or electromagnets are employed in low electric field. In sweep NMR spectrometers, the compound is irradiated with electromagnetic energy of a constant frequency, while magnetic field strength is varied or swept. Electronically, it is easier to maintain a constant radio frequency and very high magnetic field strength. By these techniques, the protons are brought into resonance one by one. The recording that single spectrum takes approximately. We consider that CW is still used in some of the lower concentration instruments, but CW instruments have been almost completely superseded by FT spectrometer. An important innovation in the field of NMR spectroscopy is the introductions of superconducting magnets that have a much higher magnetic field strength than their procedures. A superconducting magnet consists of a coil and solenoid made from a special alloy. The coil is immersed in liquid helium. The magnet has to be kept permanently at the temperature of liquid helium. To minimize the helium consumptions and increase the period between refills, and the helium tank is cooled by liquid hydrogen, which has the additional. Just you go through that schematic diagram for Fourier transfer NMR spectrometer with a superconducting magnet. This are all you go through that. What is that? Shielding and de-shielding I am going to explain. Since the magnitude induced magnetic field opposes the electric magnetic field, the strength of the external magnetic field around the nucleus is then reduced. The reduction of the external magnetic field around a nucleus is called shielding. In summary, when a compound is placed in a homogeneous magnetic field, the protons will be under the influence of different magnetic field because of any magnetic field induced when opposing the external magnetic field. For example, proton resonates in the presence of magnetic field 1014. We bring these protons is an external magnetic field is 14 giga. Now the electrons around the protons will generate a secondary magnetic field strength 50 giga. The proton is no longer under the influence of the field 14,000. Since the induced magnetic field opposes the external magnetic field, the proton is then under the influence of total magnetic field. This value is not sufficient to bring the proton into resonance, which would require the strength of the external magnetic field to be increased to 14,050 Hertz. The relaxation is said to be shield the proton. In secondary magnetic field is generated by the external magnetic field. The magnitude of the secondary magnetic field depends upon the strength of the external magnetic field, thus represented by your secondary proton is equal to sigma into H into proton. Where H is secondary magnetic field, H0 that is external magnetic field, sigma is the shielding constant. The term sigma is referred to as the diamagnetic shielding constant, and its value depends on the electron density around the protons. Hence, the protons are under the influence of the external magnetic field as well as of the magnetic field induced by electron. This means that the effective magnetic field HEFF sensed by the proton is slightly less than the external field by an amount sigma 0. Consequently, resonance frequency of protons is given by the molecules will be different as long as their chemical environments are difficult. The shielding constant will determine the resonance frequency. The shielding of nuclei can be expressed as the sum of the four terms. What are those four terms? Here, sigma is equal to diamagnetic, paramagnetic, neighboring and solution. Diamagnetic, paramagnetic, and sigma is what? Neighboring group shielding, and delta solution is the solvent shielding. That chemical shift is also very important here. Generate two more questions. The protons will have different resonance structures. Shielding and de-shielding effect or the absorption of the protons to shift from the position at which their protons would absorb. These shift the resonance of different protons at different frequencies are called the shift. Two protons are located in the same chemical environment. They will help be under the influence of magnetic field and their resonance signals will overlap. This is what NMR spectra of that what methyl acetate. CHCl3, H is replaced by hydrogen. Now, we are going to study with that. Infections of proton NMR spectrum of methyl acetate shown above reveals two methyl responsibilities for resonance, which is so that these methyl groups are in different chemical environments. One of these groups are bonded to a certain atoms. Similarly, the proton NMR spectrum of paramethyl benzene nitride shown below is showing three distinct resonances. This means that the compound contains three different protons, aromatic methylene and methylene protons. One would accept aromatic protons. The appearance of one signal indicates that the aromatic protons do not differ greatly from each other. This is the spectra of that chemical shift of that organic compound. The units of chemical shift, as we observed in proton NMR spectrum of methyl acetate, the two empty groups gives two signals due to the difference in the resonance frequency. For appearance of these 10 digits, we have to define the position of the resonance signals in an NMR spectrum. The chemical shift are measured with resonance to the absorptions of protons of reference compound. The most general used reference compound is what? Tetramethylsilane. Simply that is called what? TMS. In practice, a small amount of tetramethylsilane is usually added to the sample so that standard reference absorption line is produced. The distance between the signals and the sample, the reference signals are given in that hertz only. The following reasons given account for the tetramethylsilane is used as reference. The TMS signal, you know that tetramethylsilane is cheap and readily available compound. Tetramethylsilane is chemically inert. There are no reactions between TMS and the sample. The tetramethylsilane has a low boiling point, -27 degrees Celsius. It can be removed from the samples by operations after the spectrum is recorded. The 12 protons of tetramethylsilane produced a sharp signal even at lower tetramethylsilane concentrations. The reference signals may be easily recognized. Before recording a spectrum, tetramethylsilane is added to the sample whose spectrum is being measured. The distance between the TMA signals and the sample signal is called as a calculated shift or corresponding proton. Chemical shift as the difference or distance between the volume of the sample minus volume of the standard means, as already explained, the frequency difference delta V will increase with the increased magnetic field strength, and they are direct proportionality relations. Thus, delta V varies with the size of the operating NMR spectrometer. Now, remove the effect of the magnetic field and here just to see here. Remove the effect of magnetic field on the chemical shift is divided by the operating frequency of the spectrometer and multiplies by 10 to the power of 6. The resonance frequency for the reference around compound tetramethylsilane is set to 0 definition. Thus, the chemical shift equation will have the following atom. This is resonance regions of organic compounds, approximate protons chemical shift regions of organic compounds. The advantage of using an instrument with higher than low field strength is that the different NMR absorbs more readily separated. This will affect the appearance of the NMR spectra and simply the imperfections of spectrum. Here, these are all the functional group. These are all NMR shift, cyclopropane, primary hydrocarbon, secondary hydrocarbon, tertiary hydrocarbon. Chemical shift is also mentioned along with that functional group. Allylic means that is this one, amine RNH2, alcohol or OH, and carbonyl CO, acetylene C triple bond CH. Benzylic means CH2 along with that benzene aromatic ring. These are all what functional group along with that chemical shift. This is the graphical representation, general absorptions regions of different functional groups. The proton chemical shift fall that range 0 to 14 delta. The saturated hydrocarbon occurs in that 5 to 6.5 ppm. Aromatic protons appears in the 7.5, 7.85. These values are never exact ranges. Resonant structures, these given states can be encountered depending on the electronegativity of the attached substituents. The influence of electron density on chemical shift. As mentioned before, the circulations of the electron induces a secondary magnetic field which opposes the external magnetic field according to Lenz's law. Consequently, the strength of the external magnetic field is reduced and thus we need a higher magnetic field for the resonance of the individual protons. In the NMR spectra, the spectra of the magnetic field increases from left to right. Just this is all what that is increased electron density. What happened that resonance? In that increased electron density, the resonance is also having very high field. And that some less electron density will generate less shielding and resonance will appear at low field. The chemical shift of methylene group attached to 3 functional groups depends entirely on the electronic substituents X, Y, Z. The substituents with electron withdrawing ability will donate the electron density around the proton and cause lone shielding. Then the chemical shift will appear at a lower field. However, if the substituents are electron releasing groups, the shielding will be increased. The proton resonance will appear at a high field. These are all what different alkyl halides molecule CH3X, CH2X here. To increase the concentrations of halogen, the substituents are mentioned here. These are all some important aspects regarding to that Nmr spectrum. These are all the chemical shift containing compounds, hetero atoms. What is that? For alcohol 3.39, ethanol, this carbon, this carbon. Just you go through that book. These are all standard values. We are going to representations and we are going to follow some rules to determine the NMR value. Okay. These are all some examples. For this carbon is having 3.94. This neighboring is having only 3. 3 means that is removed by 1. That ether molecules. These are all very important. Just to go through that. Some numericals.